This Swedish inventor outsmarted Detroit with a weird free piston engine in 1928. Imagine an engine that has no crankshaft, no connecting rods, no camshaft, and no traditional valve train. Instead, pistons move freely back and forth, almost like pinballs bouncing inside a machine, creating power through carefully controlled motion that looks like chaos. At first, it sounds impossible. You might think such a machine would destroy itself within seconds. Yet in the late 1920s, while engineers in Detroit were perfecting the conventional engine design we recognize today, a Swedish inventor named Birger Ljungström built exactly this kind of engine. And remarkably, it worked. In some ways, it worked even better than the engines coming out of America's automotive capital. Picture Stockholm, in the late 1920s. The automotive world was expanding rapidly. Henry Ford had just introduced the Model A. Cadillac engineers were working on powerful multi-cylinder engines, and the structure of a typical engine seemed firmly established. Everyone knew what an engine looked like. Pistons moved up and down inside cylinders. Connecting rods attached those pistons to a rotating crankshaft. The crankshaft transformed that up and down movement into rotation. A camshaft synchronized valves that allowed fuel and air into the cylinders while pushing exhaust gases out. Hundreds of precisely machined components worked together in perfect timing. Then Ljungström stepped into his workshop and asked a radical question. What if the entire design was wrong? What if engines didn't need all of those parts? This is the story of the Swedish engineer who challenged every assumption about engine design, built a machine that doubled the efficiency of typical engines of his time, and demonstrated that the best solution is sometimes the one no one else is brave enough to attempt. It is also the story of why most people have never heard about his invention. To understand how revolutionary Ljungström's engine truly was, we need to look at what other engineers were building during that era. Internal combustion engines had existed for roughly half a century. By that time, their design seemed settled. Pistons moved inside cylinders. Connecting rods transferred motion to a crankshaft. The crankshaft rotated and powered the vehicle. A camshaft synchronized the opening and closing of valves. Everything relied on precise timing. Connecting rod bearings endured tremendous forces with each combustion cycle. Crankshafts were massive forged pieces of steel that had to be perfectly balanced. If even a slight imbalance occurred, the engine could shake itself apart. The valve train added even more complexity. Springs, rocker arms, push rods, and cam lobes all had to move in perfect coordination. By the late 1920s, manufacturers had become skilled at producing these engines. A typical automobile engine contained around 300 moving parts. But the efficiency was poor. Only about 1/4 of the fuel's energy became useful work. The remaining 3/4 escaped as wasted heat. Engineers accepted this as unavoidable. Engines were heavy, complicated, and inefficient, but they worked. Birger Ljungström saw things differently. He looked at the entire system and noticed unnecessary complexity everywhere. Why did an engine need a crankshaft at all? What if pistons could move freely instead of being tied to a rotating shaft? What if the energy produced by combustion could compress air, and that compressed air could spin a turbine to produce power? That idea led to one of the most unusual engines ever designed. Ljungström's concept was astonishingly simple. Two pistons faced each other inside a single cylinder. They had no connecting rods and no crankshaft linking them together. When fuel ignited between the pistons, the explosion pushed them apart. As they moved outward, air behind each piston compressed and acted like a spring. That compressed air forced the pistons back toward each other again. When they returned, the air between them compressed until the temperature and pressure became high enough to ignite the next fuel charge. Then the cycle repeated. The pistons never actually collided. Instead, they bounced back and forth endlessly, driven by controlled combustion and air compression. But those pistons were not just moving for the sake of motion. Each stroke also compressed air in secondary chambers connected to the main cylinder. That compressed air flowed into a turbine. The turbine rotated and powered a generator or other machinery. In other words, the pistons transformed fuel directly into compressed air, and the turbine converted that air into rotational power. The engineering advantages were remarkable. Without a crankshaft, there were no main bearings to fail. Without connecting rods, there were no rod bearings to wear out. Without a mechanical valve train, there were no timing chains, valve springs, or camshafts to maintain. Ljungström eliminated roughly 80% of the moving parts found in conventional engines. Even more impressive was how the design handled compression. Traditional engines have a fixed compression ratio determined by the crankshaft geometry. If compression becomes too high, the engine can knock or suffer damage. If compression is too low, efficiency decreases. But Ljungström's pistons were not constrained by a crankshaft. They compressed the air-fuel mixture until the conditions were exactly right for ignition. If the fuel quality changed, the pistons automatically adjusted their motion. With low-grade fuel, they moved closer together to reach higher pressure. With high-octane fuel, they traveled farther, extracting more energy. The engine essentially optimized itself automatically. For its time, the efficiency numbers were astonishing. While the best conventional engines achieved roughly 25% thermal efficiency, Ljungström's free-piston engine approached 50%. That meant it could produce the same power while consuming only half the fuel. The engine was also far lighter. Without heavy crankshafts and complex valve systems, it weighed dramatically less than traditional engines of similar output. In the mid-1930s, Swedish State Railways tested one of Ljungström's engines. A unit weighing just over 2,000 pounds produced roughly 140 horsepower continuously, with peaks reaching around 200 horsepower. Comparable diesel engines weighed nearly twice as much. Despite these advantages, the American automotive industry rejected the concept. Engineers in Detroit viewed the design with suspicion. Conventional engines were predictable. Every component moved in strict synchronization. Ljungström's design behaved differently. Its pistons moved at their natural rhythm, which could change slightly with temperature or load. To engineers trained in rigid mechanical precision, that unpredictability seemed dangerous. The engine also sounded unusual. Instead of the familiar rhythm of traditional combustion engines, it produced a buzzing vibration created by pistons, oscillating dozens of times each second. To many observers, it sounded strange and unfamiliar. At the same time, American factories had already invested enormous resources into building conventional engines. Entire manufacturing plants specialized in crankshafts, camshafts, and cylinder heads. Switching to a radically different design would have required rebuilding the entire industry. So Detroit ignored the invention. But the idea did not disappear. European companies recognized its potential. Engineers began using free piston systems in specialized industrial machines, particularly compressors and generators. Some submarine designs even adopted the technology because of its compact size and efficiency. Later versions produced impressive performance while using very few parts. Some units operated reliably for tens of thousands of hours, with minimal maintenance. Eventually, however, gas turbine technology began advancing rapidly. Gas turbines offered many of the same advantages: few moving parts, high power-to-weight ratios, and multi-fuel capability. As turbines improved, interest in free piston engines gradually faded. Then, emissions regulations introduced another obstacle. Because the pistons moved freely, rather than according to fixed timing, controlling emissions precisely became extremely difficult. As environmental standards tightened in the 1970s, the technology fell even further out of favor. Yet the idea never truly vanished. Decades later, engineers began revisiting the concept. Modern electronics, sensors, and computer control systems could manage the variable behavior that once frightened engineers. Researchers began experimenting with free piston engines connected to linear electric generators rather than turbines. In these systems, pistons move back and forth to generate electricity directly. Modern prototypes have achieved impressive efficiency levels, sometimes exceeding 40% while producing power from compact machines. Nearly a century after Ljungström built his original design, the world has begun rediscovering its potential. The Swedish inventor who once challenged conventional engineering may have simply been ahead of his time. Sometimes innovation does not fail because it is wrong. Sometimes it fails because the world is not ready. And sometimes it takes decades before the rest of humanity catches up to an idea that was already brilliant from the beginning. Today, engineers searching for cleaner and more efficient ways to generate power are once again exploring the concept of free piston engines. The design that once seemed impossible may still shape the future. And somewhere, perhaps in another quiet workshop, another inventor might already be building the next impossible machine.